working on developing next generation catalysts for the green transition. A key element in that is being more efficient at reducing CO2 into sustainable fuels and chemicals.
With Gefion, we were able to model this reaction using an enzyme that can convert CO2 into formic acid or formate, which is a chemical, a building block that can be used in many different industries. And we are developing such technology so that we can utilize this greenhouse gas towards sustainable chemistry. Enzymes are the building blocks of cells, but they are really complex molecules. So we want to understand this complexity because enzymes move a lot and they are highly dynamic systems. So a key question in our group is how can we understand these dynamics in order to develop faster and better enzymes for applications in sustainability.
Enzymes are quantum mechanical at their core, and so previously we could only simulate these enzymes and their rhythms classically. And so what Gefion allowed us to do is scale quantum mechanics to these large 100,000 atom systems, which let us really look at the heart of this enzyme. So currently we're finding improvements, but what computation allows us to do is search a much larger space, almost a galactic scale, and this lets us find, instead of good improvements, exceptional improvements in both materials and enzymes.
This is our most ambitious simulation to date. We have excellent compute infrastructure here at the university, but we simply do not have the amount of GPUs and the speed that we could get at Gefion. For this system, we needed to have very large time series so we could get sufficiently good statistics that we could see how mutations in the enzyme could improve the speed in running in reverse compared to the wild types we find in nature. So on Gefion we were able to run on 256 of the fastest GPUs out there. And that enabled us to try out very ambitious systems, but also to get statistics that allowed us to do something that hadn't been done before. It opens doors for other projects that we can do. For instance, studying how to synthesize nanoparticle catalysts and even compare to experimental observations on that.
So we have computation, experimentation, and automation coming together. And what we can do now with Gefion is run these high throughput simulations, link them to experiments we are doing in the lab, and then help improve this enzyme, which might solve a biosustainability challenge.
The team in Gefion has a lot of expertise, so it really helped us to scale up the system and also to troubleshoot at the beginning.
Access to Gefion also allowed us to train our so-called foundation models. So there we are able to describe different classes of materials, going beyond enzymes, or even looking at drug docking, completely different things than the method was originally used for. And that opens a plethora of new possibilities in science. And also, to be honest, we don't know where the next discovery will come. If it's a new drug, if it's a new catalyst, I'll take them both.
Looking forward, I will be excited to see how Gefion and AI will help us to understand enzymes and improve them to produce new chemicals, materials and medicines, thereby accelerating the green transition.
Some of the most ambitious projects that we are dealing with now require parallelization over a very large number of GPUs. This requires a very fast network. It requires fast access to the hardware disks, and this is something where Gefion is stellar. So this is one of the ways that will allow us to describe systems of complexity that I can't even think about now. And so I'm really looking forward to exciting years as we grow and Gefion grows.